Yeah, so today I'll talk about use a visualization tool that we came up with to study linear versus nonlinear association between an exposure and outcome. I'll go into like two case studies of what the specific exposure and the specific outcomes there, but we hope that this tool would be applicable to any association study. And so I'll first start with some limitation of using a linear model. I mean, it's a really simple approach to use. You just run one model, you get one value out of that, right? A beta coefficient to interpret if it's positive. That means that as the exposure increases, the chance of the outcome or the measurement of the outcome also increases if it's negative. And then it's the opposite interpretation. It's easy to interpret, just one value, right? But we found that it's very limited in capturing. It's very limited in capturing the associations, as it's either strictly increasing or strictly decreasing. As another example, if a shape is actually something else, it could lead to a null association if you use a linear approach. So let me just demonstrate with this animation right here. And so let's take the concentration of vitamin A on the x-axis here. So this vitamin A is involved in important function, just like immune function, vision, reproduction, cellular communication. It supports cell growth, differentiation, plays an important role in normal formation and maintenance of, say, the heart, lungs, kidneys, and other organs right here. And it's mostly found in like animal products, dairy products, fish, and meat. And so and then on the x-axis, let's say it's some sort of like relative risk for maybe it's like heart disease or mortality. And so it ranges from low risk to high risk. And so maybe the data points looks like something like this, where when you have lower concentration of vitamin A, you're at increased risk for say a given outcome here, let's say mortality. And then you want to be in the sweet spot right here, a good normal range of vitamin A. But if you have too much vitamin A, that can also lead to a risk. And so if you see data points like this, you would think that, I need to click, that the curve would look something like this would be the best fit, some sort of quadratic parabolic curve that would best describe this association when if you're trying to fit a model to these data points right here. But if we use a linear approach, it would to minimize the difference between this line and the data point, it will look like a straight line right here. And so this would say that across whatever it's saying, whatever amount of vitamin A's you get, there's no risk involved. The risk is the same throughout. So here I'll show an actual. So this is just a kind of as like a demonstration of concept, kind of a sort of pseudo example, but I'll demonstrate with like real data that this actually happened, where when you use a linear approach, when it's actually a U-shape, a nonlinear association, the association, the effect of this, say, exposure of vitamin A on an outcome could be null, or actually is null. And so another limitation we found of using a linear model is there's going to be, and so here we did an association study looking at looking at the association between physiological indicators and all-cause mortality. And then we looked at the prediction performance, and we did this for, say, concordant index and the network R-squared. So the concordant index is like an AUC counterpart when you look at mortality data. And then we did it for one linear model and two nonlinear models. And what you see is that for the concordant index, usually the linear model is very like on par with other nonlinear model in terms of prediction performance. And then when you look at this R-squared over here, you sometimes then see that the R-squared, the prediction performance for the linear model is slightly better than the nonlinear model. And so we take something like body mass index, and we use only this criteria, only the prediction performance, to deem like what is the more appropriate model, linear versus nonlinear. If you just straight up say like what's the max average prediction performance for BMI, you would select the linear. And so we'll look at the consequences of just selecting your most appropriate model based on prediction performance instead of looking at the actual shape of the association. And so with that, I'm going to today I hope to demonstrate the utility of the stairway plots to study these linear versus nonlinear association between a exposure of interest and an outcome interest. So 2 case studies right here. So first one is a publication of ours. Here I characterize linear versus nonlinear association between 27 physiological indicators. So these are like clinical indicators right here, such as like BMI, weight, and then all-cause mortality. And here we use the stairway plots, this visualization tool that we developed to, one, identify participants who are at increased risk for mortality, but also evaluate whether the clinical thresholds are actually informative of distinguishing those who are at low risk from those who are at high risk for mortality. And then I'll show a second study that we're currently working on right now. And here we're looking at the relationship between chemical exposures and cancer-specific mortality. One, to identify what are like the measurements or concentration associated with increased risk for cancer death, but also to identify maybe a potential new carcinogen. And so with that, we'll move on to the first case right here. And so just some background on this study right here, looking at the association between physiological indicators and all-cause mortality. And so clinical thresholds, what they're used is to identify, to kind of triage participants who are at high risk versus low risk for, say, like poor health, and also to determine the allocation of healthcare resources. And so, for example, for BMI, we're told that the healthy range that our BMI should be is 18.5 to 24.9. But sometimes these clinical thresholds could be chosen arbitrary. For example, the thresholds for BMI was actually defined by the World Health Organization in 1995, and it was actually based on looking at these associations between BMI and all-cause mortality. But then there's been mounting evidence. This one paper, meta-analysis looking across different population, relooked at the associations in the more recent years, and saw that this association has really shifted. And so we'll show that in our study, like how much it's shifted and how that can influence the relevance of these clinical thresholds. And so if we want to define like relevant like risk threshold, clinical threshold, to distinguish those from low risk to high risk to allocate resources appropriately, we really need to get a hold on like these associations. And so especially assessing whether these associations are linear or nonlinear. And so the methodology we use here is to assess a safety association. And so this is a regression model here. As we're studying mortality, we're looking at mortality data, we use a Cox proportional hazard model. And so the main predictor is the physiological indicator, and we adjust for age, sex, and race as of now. And then for the physiological indicator, we have a model. We leave it as is, and that helps us study the linear association. For the Bumtile here, this is where we break up the distribution in 9 pieces, and then choose a group to be the reference group. And so this is a common or a more canonical methodology here, where when you want to study nonlinear association, you break up the distribution of your exposure. Here, our exposure being physiological indicators you transform it into a categorical variable. And then for the spine model here, so this is a more flexible nonlinear model. And so this right here is you can think of it as some sort of like weighted sum of cubic polynomials. So here it allows just like more flexibility in looking at the shape of the association. And then to look at the prediction performance and to evaluate for overfitting, we did tenfold cross-validation, and then we use these grids, so not cross-square, AIC and concordant index, do that. And when we try to define a confidence interval or range around these measure right here, we did bootstrapping for 1,000 replicates. And so we get this right here. So I'll show this again. And to reiterate that if you, let's just like focus on BMI right now, but again, going through, you know, the standard protocol for choosing the appropriate model based on prediction performance, we see that the linear model performs fairly on par when looking at the coordinate index with the other nonlinear model. But then when we look at another a prediction performance measure, we see that the linear model performs like slightly better than the other two nonlinear models. And so here, so let's take a look at like the consequences if we went with a linear model when studying the association between body mass index and mortality. And so I'll put so here's, so on the x-axis I show the kind of the distribution of the body mass index, and then on the y-axis here, this is hazard ratio. This is a measure from our model looking at relative mortality risk. And then these pink lines right here, the lower one, this indicates the lower range. And so this is like 18.5 to 19 BMI, so that's on the lower range. And between 18.95 and I think 24.5, this is the range. And so the arrows indicates when you're outside that normal, that range of that normal range. And so, and then this red line here shows the linear model here. And so what we see right here is this is saying that, oh, regardless of what your BMI is, regardless of what your weight, your ratio of weight versus is that your weight versus height is, there's no risk for mortality. This is nonsensical. Like we intuitively know that there is consequences when we eat too little or eat too much or do not have enough like skin, fat, all those necessary things to function. And so this right here, we show a real life example of how using a linear model could potentially be dangerous. And so this model is just really limited in capturing the shape sort of leading to like a null association. And so now we add in the more canonical model, the common method of let's use the 11-tile, 9-tile models. And we see here this U-shaped curve. And so here I'll interpret here. So there's no box around 6, as 6 is the reference group. And so with 1 right here, how you interpret this is those between, I think like 17.7 and a body mass index, I think of maybe around like 22. Their risk for mortality is about like, I think 75% higher than those who are in this range right here. So I think that looks like about 28 to maybe about 30 right here. And so this might make sense that those who are underweight would be at increased risk for mortality. And then on the other end of the spectrum, when you say are overweight or obese right here, and so if your BMI is above 30, 35, your risk for mortality, that looks about like 50% higher. It's 50% higher when you're compared to being in this range right here. And so here's the nonlinear horizon more. To me, it makes more sense of the association between BMI and mortality. And then we add in the spline model here, the more flexible model, nonlinear model, and we see that the nonlinear models agree with each other. And so based on this, if we went with the prediction performance alone and actually selected the linear model, it would lead to nonsensical results. But when we actually compare the actual shape of the association between the linears and nonlinear model, we see that for interpretation for any type of medical, clinical, or public health decision making, it would be more informative. So that's one example. And so we did other examples. And so I guess I want to note here is how in 1995, when they did a study like this, looking at association to BMI and mortality risk, the participants with the lowest risk were in this range, so this 18.5 to 24 right here. But do you notice how now with this data, and so this data ranges from 1999 to 2014, we see that the risks here, the participants with the lowest risk are in this like 22 to about 30 range. And so we see how this like this range of being a normal weight is changing. It could be to something more secular, as maybe our health infrastructure is getting better over time and being able to treat those who are more obese. It costs could just be like changes in diet. So basically a lot to figure out here, but we do see like there's this change from what it was in 1995 to, like I say, currently. And then oh yeah, good at time. And then it has another example. So estimated GFR right here, so glomerular filtration rate. So this is a clinical biomarker of how well your kidney function. And so what's usually the case is that if your kidney function is below 90, that indicates some sort of chronic kidney disease. If it's above or higher, it indicates a decreased risk for having chronic kidney disease or kidney failure. And this pink box, and so you don't want to be below 90. So an interesting thing we found is if you looked in the Bovtile model, when you're below 90, you're at an increased risk for mortality about, that looks like 70% right there, compared to in this range right here. But that risk right there is not as high as when you have very high levels of GFR right here. And so with when you have GFR levels above like 120, your risk of mortality is like 150 times, 150%, or that's almost like 2 times higher. And then here up to almost 3 times higher compared to those within this range of about 64 to 80 right here. And so we saw this and say like, oh, you're based on the clinical threshold, you would be at risk. You are at risk when you're below 60, but the current clinical threshold does not take into account that when you have really higher levels of GFR, you are also at increased risk, but but the risk there is even more than when you have lower levels. And so when we look at the shape of the association and actually compare the current clinical thresholds with this, we see that this example here shows that instead of considering the need to consider 2 bounds, that being lower and higher leads to increased risk for mortality and not just only being lower. And so for the most part, when we over this for the 27 physiological indicators that we looked at, we observed that almost all of the association between those indicators and mortality were nonlinear. There were here I show an example of how the association between height and all-cause mortality is linear, as we kind of see like a general agreement across the different models. Here we see that the linear model aligns well with the other nonlinear models. And so we deploy this, and so here I only had time to show a few, but here we develop an app to look across all the different physiological indicators. And so yeah, so here's a link where click on the link and you can explore that such things are an interactive app right here. And so in summary, when we use these stairway plots, when we look at the states associated between linear and nonlinear models, we observe that only height and 60-second pulse were the only clinical indicators. That's the linear association. Everything else showed a nonlinear association. The stairway plots also show that there's a lot of clinical thresholds that just don't align with the mortality-based thresholds that we found. And here's the list of them right there. And for a lot of those indicators, as we saw with GFR, it's not enough to have one bound. Sometimes there's a need to have 2 bounds, showing that if you're at lower levels or at higher level, you are at increased risk. With that, are there any questions? Okay.
Nothing in the chat box yet, but if anyone does have questions, put it into the chat.
Okay. I think, okay, if that's the case, let me move on to our next case study and looking at these relationships between chemical exposure and cancer-specific mortality. Here we do it for 241 toxicants. And so the current lab that I'm in, the Colosina lab, they're interested in really using data-driven approaches to like prioritize like which toxicants, which chemicals are important in initiating cancer here. Because what a lot of toxicology studies, what they tend to do is like fit their favorite chemicals, and then they'll choose these really high, choose these concentration, like dose these cells or at really high doses, and these doses right here could be like several orders of magnitude above what the human population is actually exposed to. And so what we want to do here is we want to like characterize the risks associated with these chemicals that are actually found in the human body. And hopefully by doing this, we can help prioritize like which chemicals should be used for further toxicological evaluation to understand how this chemical could lead to some sort of not only initiation for cancer, but also could provide some sort of insight into leading to death from cancer. And so with that, I'll switch over to my Shiny app over here. And so see here, oh, what's that?
Question came in the chat, so I thought before you get to answer it. So the question from Nigel is, can you describe more how the reference point in your plots and method is selected? For instance, in your overall risk versus BMI analysis, the reference point was chosen outside of the clinically healthy range. What is the significance of your choice?
Oh, yes, that's a good question. And so right there, how we chose the reference point right here is that we chose the concentration that is so associated with minimum mortality risk. And so that would be our baseline here. And so that would just help with easier interpretation. You're welcome. Let me switch over to my Shiny app. And so for here, to be honest, I still need to do like quite a bit of work on this, but here I chose the minimum concentration to be the reference group, just to so we can kind of see how that changes in a sequence. And so and so here I show the kind of shape of the association with blood cadmium right here, and cancer specific mortality. And so the reference group is let's look at the Nguyen file, so the boxes here. So the reference group here is 1. And so if we look at 8 right here, this is saying that if a participant with blood cadmium levels between 0.63 to 1, so this is in about the 80 percentile to I think about the 91 percentile. On average, their mortality risk is 78% higher than those who have some of the lowest concentration of blood cadmium right here. So this ranges from 0.7 to I think 0.15, 0.14. And so 78% to me is really high. Usually we are already concerned when it's a 10% increase from baseline mortality risk. And then when we go even further for when 9, and so here the range goes from the range in blood cadmium here goes from 1 to 93. And then on average, this the mortality risk for cancer is 2 times, almost 2.4 times higher than those with baseline mortality risk. So that's like that's really high right there. What else to say here? I think another thing is that, yeah, these concentration right here, even though it's in even though it's found in kind of the upper, those with some of the highest levels in the 80 percentiles or more, these are not like, actually, these values right here are not like astronomically, like 0.63 is actually still a small concentration of blood cadmium. And so for now, I still need to run a lot of these shapes for other models right here. But when I show my lab mates who are toxicologists, it inspired. I would say like they're really excited about the results, as it indicates that they would want to do more experiment on this to understand. So maybe I'll back up with this. So they want to do more experiments to kind of confirm whether this association here is where blood cadmium here is a causal factor of cancer mortality. And so here we can only say it's an association. So what they would have to do is take this chemical right here, expose it to certain cells right here, and then see how at these concentrations right here could lead to the onset of cancer, and then lead to how, and then study how the cancer right here could spread, could metastasize. Because when we see cancer metastasis, this is highly linked to cancer mortality. And so in summary, this plot right here enable us to really see how like identify like which chemical concentration, I guess, for like by which concentration, which measurement for which chemical is associated with increased mortality risk. And this could lead to experiment to confirm one, how such chemicals could be the onset for cancer, but also could lead to cancer death. And hopefully when I run through, so here I only ran it for four chemicals, but hopefully when I run it through the other 241s and look through all those results, we can start to identify like, oh, which of these chemicals should be further tested to understand this mechanism of being exposed to this chemical leading to cancer, and then leading to cancer death. So in conclusion, these survey plots really enable us to characterize the state of association, and it really helps to have linear and nonlinear models on the same figure. It really enables us to identify measurements of an exposure that associate with increased risk, as we saw with, we're able to say like at this concentration or this measurement of this physiological indicator, this is the risk associated with it, or these are the concentration of this chemical associated with the increase right here. And so still current work right here, but we hope to deploy this methodology in an R package to really study association for any exposure and any outcome. And so this was suggested by one of my mentors here, because we plan to really apply this methodology to study the relationship between any physiological indicator and other clinical health outcomes, to really understand like whether these current clinical thresholds are relevant in distinguishing those with low risk versus high risk of, say, any of these health outcomes. And then for another project here, I guess the point that comes up, like when looking at chemical exposure and mortality, it's like isn't that quite a reach to look at that, because the hypothesis that when you're exposed to a chemical, the chemical goes in your body, moves around, probably does a lot of physiological dysfunction in there. And so wouldn't it be more conducive to study how does the chemical affect your physiology in a way that may induce cancer or may induce death? And we acknowledge that. And so the reason why for the last case that I showed, the reason why we chose cancer mortality, this kind of ultimate health outcome, is because we know some of the data set that we're using, it could some of the outcomes could come before when the chemical was measured. And so if I do association on that, it's really hard for me to interpret, like, that, right? Like, versus when with cancer recipient mortality, we know that the chemical exposure occurs before the mortality. So when we look at it, when we see a significant association there, we could to better get at, help drive experience to get at this association in a more causal manner. And so, but then again, we want to be able to also run these analyses right here to understand how the chemical exposure could perturb physiological dysfunctions in a way that could lead to mortality or cancer mortality. And thank you so much for listening and coming to my talk.
Yeah. So if anyone has any questions, you can either put them in the chat box or unmute yourself and ask.